here's another system that involves energy and momentum and angular momentum. This is a macroscopic system, something we might actually see. And here's the idea. We have two, it says pucks, they're discs, okay? Two cylinders to look like about the shape of a hockey puck. They're sliding on ice. And one of them has a little nail in the center and a string attached to the center. And you're pulling on this string with a force F. And the other one, so you're looking down on the ice, okay? The other one, same mass and everything, but it's just got the string wound around the outside. And so you're pulling with a force F, which is applied where the string comes off the puck. And so the question here is, you pull on each of them with exactly the same force, F, for 3 seconds. So what's going to happen? Just try to imagine it. What's going to happen in the next 3 seconds? So okay, big vote for 2 is going to move farther than 1, with the small votes for the other things. So what's going to be the big difference in what you see in these pucks? One's going to be rotating, right? Okay. So now that you've just tried to imagine the situation, let's bite the bullet and try to apply some physics principles. So same question, except we're going to use the momentum principle and just see what it says. You've already told me what you think is going to happen, so let's just see what the momentum principle applied to these pucks says is going to happen. So we've got a delta t of 3 seconds. They're both starting from rest. What does the momentum principle say is going to happen after 3 seconds? Same force, same time, momentum principle. So those people who are not actually asleep. So there's a big vote for 3, which is they should move the same distance. And there's one extra step in that, because of course the momentum principle doesn't tell you distance, it tells you momentum at the end. So for puck number 1, we say P final is P initial plus F net times 3 seconds. And initially that was 0. So the final momentum is going to be equal to the net impulse applied, non-zero plus x direction. Okay. So puck 2, where F net, what's F net, by the way? Is that the force F you're pulling with? It is, isn't it? Because although there's a gravitational force down, the ice is exerting a normal force up, and so no action in the y direction. So we can just say F here. Puck 2, P final, P initial, plus F times 3 seconds. Looks like P final is going to be 0 plus F times 3 seconds. So the final momentum is going to be the same. Final velocity is the same. Average velocity is the same. They should move the same distance. Well, that's not what we said originally. What is the momentum principle not telling us about? That's right. It just tells you about the translational motion of the center of mass. It doesn't tell us anything about rotation. So the momentum principle is saying that their centers should have moved the same distance. It's not saying anything at all about rotation. We know that number 1 is gonna be rotating. What would we have to do to find out about rotation? angular momentum. And so for puck 1 here, we'd write, we're really interested in rotational angular momentum. Final is rotational angular momentum initial plus the net torque and the net torque is not zero, is it? So we have, here's this force F. It's not applied at the center, so the net torque is not zero. So it looks like it's going to be 0 plus R cross F times 3 seconds, where R, what's R? That vector R. So we're applying this torque, R times F, in the, well, here's R, there's F, minus Z direction, right? So after 3 seconds, it should be spinning, whereas puck number 2 is 0 plus, what's the net torque on puck number 2? 0. Okay, so it says that that should be spinning. Which one has more kinetic energy? Well, let's figure it out. Okay, puck 2, that's a simple one. Net torque? Okay, so why is it the net torque 0 on puck number 2? Because remember, so that's a good question. Remember that the definition of torque is that it's R cross F. So for puck 1, here's F. There's R. For puck 2, here's F. What's R? R is 0, isn't it? Because R, we're taking torque about that point, so we have R is 0. Yeah, the cross product is not defined when one of the vectors is 0, is it? And that makes intuitive sense, because pulling from the center, which way would it make it spin? It won't. So that's why it's 0. But let's think about kinetic energy. For puck 2, K total. Do we have translational kinetic energy? Yes. Do we have rotational kinetic energy? For puck 1, we have translational kinetic energy. We also have rotational kinetic energy. Are the translational kinetic energies different? How do we calculate translational kinetic energy? Yeah, so it's a half mv center of mass squared. So here we've got a half times the mass of the puck times the speed of the center of mass squared. That's this. Here we have a half mass of the puck. V center of mass is the same. Yeah, we said it was because the momentum change was the same, right? So we have V center of mass squared. And then we have this rotational kinetic energy. So it actually should have more energy. Now that's interesting. Wonder where that other extra energy came from. Let's just look at a program that, so this is a VPython program that actually predicts what's going to happen to this system by applying the momentum principle and the angular momentum principle. So here are the two pucks. They're not purple and they're not red and blue, are they? They're okay. Here are the two pucks. Same force. That's the arrow, red arrow. That little bead is your hand attached to the string. So let's see what it says is going to happen when we start it going. So the string is paying off the top puck. And it started rotating. They did move at the same rate. Was the amount of work done the same? They moved the same amount, but how far did your hand move? You're doing the work. You're pulling. Let's look at it again. The yellow dot is your hand. How far is your hand moving? Your hand moved farther for the top puck, didn't it? So you exerted a force F for the same time, but through a greater distance. And the work you did, energetically, the work you did on the bottom puck just went into translational kinetic energy. But the work you did on the top puck was more because it went into translational kinetic energy and rotational kinetic energy. Well, if you did the same amount of work, you would have either had, how would you manage to, so the question is, what would happen if you did the same amount of work on both? Well, it seems like there's two ways to do the same amount of work. If you're exerting the same force, then you're going to have to do it for a shorter time, aren't you? Or if you're going to do it for the same time, then maybe you're going to have to change the force. Smaller force or something. So let's see what happens in real life. Let's actually look at a video.
Here we have equipment that's sort of like two pucks sliding on ice. What we really have are two heavy pulleys riding on two carts that will roll on these long aluminum tracks. One of them we're going to pull from the center. One of them we're going to pull from the edge wrapped around it. I've got them locked here for the moment so they don't move. You'll see that there are little yellow tags on here so that you can see how far the piece of string moves, in particular as it plays off this pulley as it moves. So these guys are going to move down here. What's moving them is the strings come down to pulleys, come up over these pulleys, come over those pulleys, and down to what's called an idler pulley, from which we'll hang a weight, which will then pull down. And this arrangement assures that the force in that string and the force in that string are exactly the same. So we've contrived a situation where we're applying the same force to both of these pucks, one pulled from the center, one pulled from the edge. And so we'll want to then see what happens to the motion of the pucks and also to how the little tags on the strings move. What I'm going to do is I'm going to release both of these carts, and the strings are going to pull, and what's going to pull them, as we said, is that hanging weight down there at the end. So here I go. I'm going to let go now, and you see the weight starting to fall, pulling on both of the carts. Here we have the two pucks. One can rotate, one can't. This one here is pulled from the center. This one is pulled from the edge with the string wrapped around it. We also have little plastic flags attached to the strings so you can see how those move. And for the rotating one, some string is going to pay off this being wound around the edge. So that could move in a different way. Watch how the flags move and watch how the centers of the two pucks move. We're going to apply the same force to both and a release. And here we go. And you see that the pucks are moving together. The centers are moving together. Now, eventually, the weight hits the floor at the other end. But for this long motion here, the centers moved together. The flags did not because they were pulling more string off the rotating puck, and that extra work went into making it rotate. Okay.
So it really happens. And we do need more than one principle to analyze the motion in detail and predict what's going to happen. Notice that the momentum principle, at this point we can reflect on what we meant by a universal principle. The momentum principle still works, even though these things are rotating. It tells you about the motion of their centers of mass. So the momentum principle always applies. It just doesn't tell you everything you need to know. So the angular momentum principle needs to be invoked to find out how fast it's going to spin, or you can use the energy principle with a sort of careful analysis. If you're interested, you can read the second half of Chapter 9, which talks about a systematic way of doing that analysis called considering a point particle system, where you can actually figure out how much energy is going into rotational energy. Well, you saw. What did you see? But the momentum principle, all the momentum principle tells you is what the final momentum is going to be. And the momentum principle said the final momenta after some number of seconds would be the same. And that's what you saw. They started from rest, and they speeded up together, so they were always going exactly the same speed. And therefore, because their speeds were always the same, they'd moved exactly the same distance. So the momentum principle said the change in momentum will be the same for both, and therefore they should be moving together. And that's what happened. Well, that's not the question we're asking, right? I mean, that the string thing is just a way to apply the same force. That whole string and pulley thing is just a way to apply this. Make sure you're applying exactly the same force for the same time. And it's a property of strings that unless they're sticking to something, that the tension in the string is going to be the same throughout the whole string, even if it goes around a corner on a pulley. So we ended up with momentum, angular momentum, and energy again. So three principles rule the macroscopic world, and in the microscopic world you need the fundamental assumption of statistical mechanics.